Hello, everyone. This is Brian again, and we're going to talk a little bit about basic chemistry. I hope to get through about half of this, and then maybe start the other half when I see you again next week. Hopefully, everyone is staying warm. I know there has been a snow day all this week. I know for my South Campus people, I haven't even seen you yet. So hopefully, barring any snow or sand or hurricanes, I will hopefully get a chance to meet you guys. Okay, as I stated before, you will be expected to have gone over lecture one, and I will go over a little bit of lecture two. Um, in class, we will do a brief review of lecture one and lecture two, but I'm really expecting that you would have had a chance to look at the videos as hopefully you're doing now. Okay, so let's get started with basic chemistry. Okay, so hopefully most of you have learned this in elementary school or maybe middle school about matter and energy, but matter is anything that occupies space and has mass, right? So just kind of make sure that you know that that is on your study guide for you to know. Matter can exist in one of three states. It can either be a solid, right, and hopefully you know has a definite shape or volume. It can be a liquid, right, has a definite volume, but not necessarily a definite shape, and or gas, right? And then neither has a definite shape or volume, right? So solid, liquid, gas, right? And so matter can be changed, and so matter can be either physically changed or chemically changed, right? So if it's physical change, that means you don't really alter the basic nature of a substance. And then a chemical change is if you were to actually alter the chemical composition. So to give you an example of this, let's say that I had a glass and I were to smash the glass against the wall, right? Um, and of course, as I smash the glass, the glass is in itty bitty pieces. Well, do you think that would be a physical or a chemical change? Well, hopefully you would have said that would be a physical, and it would be a physical change. Another example would be if I had a sheet of paper and I were to burn it, right? I were to kind of take a lighter and I burn that sheet of paper. Well, that wouldn't necessarily be a physical change, it would be a chemical change, right? Because I've actually altered the composition of the substance, right? And I know should be all review. I'm sure that many of you have talked about these concepts, matter and energy. Oops, I kind of crossed it out, but in elementary or middle school. And if you need any help on this concept, don't hesitate to contact me. Okay, so this is another concept that I'm hoping that you have had in elementary or middle school, and that's really about energy, right? And energy is sort of this really amorphous concept, but it really is about the ability to do work. And again, work again is a very physics definition, but its ability to sort of to change a system by force, right? Energy by itself does not have a mass, nor does it take up space, right? So that's something that you do want to know, hint, hint, hint. And there are two types of energy that we're going to be talking about. There is potential energy, and potential energy is like sort of holding a ball. So if you're climbing up the stairs, for example, that's potential energy, right? And that's as you're going up the stairs or as you're holding the ball, that energy is inactive or being stored. And say that you come down the stairs, right? That will be kinetic energy, right? And that's when energy is actually doing work, right? And in this case, the woman here is holding a ball, and when the ball is just sort of being held, that's potential energy. But when she lets that ball go, as so, that will be kinetic energy, right? So kinetic energy is when that energy is actually doing work. That potential energy, the energy is there, but it's actually stored or inactive. So some other forms of energy will be that I want to talk about will be like chemical energy, and chemical energy is going to be found in chemical bonds. And the most popular one that we're going to be talking about will be ATP. And if you don't know what ATP is yet, it's okay. It's how our cells do work. They take ATP. Actually, ATP stands for adenosine triphosphate. You don't need to know that, but just know that it has three phosphate groups. And when our bodies break off a phosphate, turning it into ADP, adenosine diphosphate. So it's turning it from three phosphates to two. That breaking off of that phosphate releases energy and releases energy. And the reason it releases energy is because energy is stored within the chemical bonds of molecules. And I'm sure if you've taken chemistry, which I think most of you have, or at least have been exposed to it in, or has been sufficiently exposed to it in um, high school, that you should know these chemical bonds. The bonds that make up molecules have energy within them. The other type of energy would be electrical energy, and this is actually one of my favorite ones. And electrical energy is just really the result of movement of charged particles, right? One of the best examples I like to talk about is really how our body generates electrical potentials, right? So, for example, if you're listening to this recording, or you're looking at this on your screen, your body is actually using sodium and potassium to actually generate electrical currents that then signals from your retina, which is in your eye, all the way to your brain, right? So again, the electrical energy, right, is just the movement of these charged particles, right? And a charged particle would be like a sodium, right? And I'm kind of trying to draw this really nicely. It's really hard to do, like sodium or potassium, right? That's one, right? And there's even other ones, right? Yeah, there's even like chloride, right, which is like a Cl minus, right? Again, you don't need to know these. You don't need to know these in any detail right now. I just wanted to just sort of show you what a charged particle would be, or a charged atom, right? And it's a movement of the sodium, potassium, chloride that actually generates electrical currents in the body. Okay. The other type will be mechanical energy, and you probably know more about this just generally, right? Mechanical energy is when energy is directly involved in moving matter, right? So, an example of that would be like if you were riding a bike, right, and your foot is on the pedal, right? Your foot is where you're going to be generating that energy, and it's actually going to be moving the pedal, which will be matter, right? Which is made out of matter, right? So mechanical energy is when energy is directly involved in moving matter, right? So it's going to be directly involved in moving matter. Right. Radiant energy is actually really, really cool. Radiant energy is obviously from the sun, right? So if we have our little sun here, and the radiant energy actually travels in waves. And the only example of radiant energy would be the sun. Okay, so just know that you should know these forms of energy: chemical, electrical, mechanical, and radiant. Just being able to just identify them and to be able to list them will be sufficient. And remember, if you have any questions, see me, or make sure that you're looking on your review sheet, which is posted on Blackboard. Okay, so what I want to talk about here is ATP, which is extremely important. And again, just being able to recognize that ATP stands for adenosine triphosphate is fine. Knowing that it has three phosphate groups, one, two, three, is kind of key. But the main point of ATP is that it traps the chemical energy from the food that we consume in those bonds. And in fact, when we have ATP in the cell and we want to do something, say like move your mousey, or to talk, or to move around, this ATP is actually turned into ADP, which is here, right? So ATP goes into ADP. And the byproduct from that conversion of ATP to ADP will be energy, which is pretty cool, right? And our body uses this energy to do stuff, right? Whether it be to move, whether it be to eject things from the cell, to bring things into the cell, to perform critical bodily functions. So ATP is very, very important. In fact, if you had a mutant power in which you were to remove someone's ATP, they would die, right? So you would be kind of a criminal, right? So ATP is important. For now, don't really dwell on it too much, other than to say that this is a form of chemical energy, right? And this chemical energy is very important because this is actually how our body is able to do its necessary body functions for us to live. Okay. So looking at matter, the composition of matter, all matter is going to be consist of elements, and and elements are sort of these fundamental units of matter, right? It's almost like a Lego, right? If I make a Lego of a box, right? The simplest unit of that box would be a Lego, right? And the simplest unit of matter would be an element. An example of an element would be like oxygen or carbon or hydrogen or nitrogen. And if you ever see the periodic table, which I think it's going to be in the next few slides, these contain a complete listing of all the elements that are known to man. And this is the periodic table. Again, you will never be tested on a periodic table. I'm never going to plot this periodic table and ask you to do anything or anything like that. But just being able to know that this is the periodic table with all the elements is sufficient enough. And we'll revisit this in a bit, but I will just show you that you have your hydrogen atom here, right, which is very, very simple. And then the other important one would be your carbon, your nitrogen, and your oxygen. And of course, a lot of these other elements are important too, like sodium and magnesium and potassium and calcium. Again, all those are very important. But when we're talking about sort of the organic elements, we typically think of our carbon, nitrogen, oxygen, and hydrogen when they all kind of come together. And again, the most important thing when we think about organic molecules will of course be the presence of that carbon, and we'll revisit that in just a few slides. Okay, so again, this is from your book, and this is just kind of a listing of the common elements of the body. I just want you just to be familiar with them. Again, knowing you're not going to be tested on the role necessarily, right? Though it is good to know. I definitely would never ask you the percentage of the body mass, so you do not have to know that, but you should know the element and you should know the atomic symbol, right? And again, I'm sure that you've talked a little bit about this because to take this class, you need to have taken chemistry. These are some other common elements. These are not, so again, just kind of knowing, again, the atomic symbol and the element is sufficient. Right, so the element and atomic symbol. So you have calcium, though hopefully you should know that calcium will be found in bones. You have sodium, which is going to be help in conducting nerve impulses. And chlorine, you don't really necessarily need to know. Magnesium, iodine, iron, just kind of keep those in the periphery, but you should definitely be familiar with calcium and sodium, and chlorine too, right? Though typically with chlorine, it actually exists in the body as chloride, right, in its ionic form. And again, if that seems like esoteric to you right now, don't worry about it. It's not something that you're going to be tested on, but just know that we don't have like a bunch of chlorine floating in the body, as it were. It's in its ionic form as chloride. So atoms are really cool. In fact, they remind me of sort of the planets revolving around the sun. And inside of an atom, you have a nucleus, and the nucleus is going to contain a proton and a neutron, right? So that's what the nucleus is going to contain. And I can actually put nucleus, and don't laugh at my handwriting using this mouse. And the nucleus is going to have the proton and the neutron. The proton is going to have a positive charge, and the neutron is going to have a neutral charge. So there's no charge. The neutron has no charge. The proton has a positive charge. And the electrons have a negative charge, but they're going to be on the outer ring, right? So they're going to be encircling this nucleus. And I have a picture that is going to help make that clear. The atomic number is really the number of protons in the nucleus, and if you have 5 protons, for example, you're going to have 5 electrons. This is why it says it indirectly tells you the number of electrons in an atom, and the reason it tells you that is again, the protons are going to always equal the amount of electrons, right? You're always going to want to have that balance there. And the atomic weight is just the mass of of an atom, and this is if you take the mass of the protons plus the mass of the neutrons here. Okay, and again, for these two, atomic number and atomic weight, you just need to be able to recognize where they are. So this would be your atomic number here, and your atomic weight, I'm going to kind of draw a little arrow there, would be there. That will be your atomic weight, right? So being able to recognize them and to be able to define them is fine. Other than that, this isn't a chemistry class. We're not going to dig too deep into the anatomy of the atom. Okay, so I actually love this. I love this slide, and I don't think it's in your book, though it may be in your book, but I don't think it's in your book. But what I love about this slide is that it actually shows you very simply the charges, right? So a proton is going to have that positive charge, like I told you about. That neutron is going to have that neutral charge or no charge, so it has no charge, and your electron is going to have a negative charge. All right, and so just kind of keep that in mind there. And it reminds me of a joke I had listened to on it was a sitcom called Big Bang Theory, and one of the guys, I think his name is Sheldon, he got up and he said the joke went something like a neutron walks into a bar and the bartender says, "For you, no charge." Right, and I thought it was really funny, and the reason it's kind of funny, at least to me, and it should be hopefully funny to you, but if you don't get it, the idea of it is that a neutron has no charge, right? So you wouldn't have to pay for the alcoholic beverages at the bar. You get it? Yeah, I thought it was pretty funny too. Anyway, so the location of the proton and neutron are going to be in the nucleus, right? And the nucleus is really just in the middle here. So I'm kind of circling where that nucleus is, and the electron shell is going to be on the outside here. Right, and again, and I forgot to mention in the other slide that the only thing that actually has mass here will be your protons and your neutrons. Okay, the difference between A and B is that A is going to be sort of the electron cloud model. So there's a model, the sort of the cloud model of an atom, and this is a planetary model. And we'll talk a little bit about the differences between those in just a moment. Okay, so what we just and so the planetary model is a very simplified model. In fact, if you're a chemist or you love chemistry or you had a really strict chemistry teacher like I did in undergrad, they hate the planetary model. They think the planetary model is childish, that it doesn't really say anything. I personally like the planetary model, but they have a point that the planetary model is kind of inaccurate because we really don't know where these electrons are in the orbitals or surrounding them, right? If you're a chemist or again a strict chemistry teacher, they probably love the orbital model, and the reason they like the orbital model is because it sort of solidifies in picture form that we really don't know where these electrons are in outside of the nucleus, right? So we may have an idea of where they may be, but we don't know precisely where they are, right? I will always be using the planetary model if I were to ever test you, but the planetary model is very good. Because in my opinion, because it helps students learn, right? So once you learn the planetary model, you go to the orbital model, right? But just know that there are two different types. And again, how this PowerPoint thing works, I can't go back. I wish I could. Actually, I just try to click back and it says no. So I can't go back to show you other than to say can go back if you go and look at your notes on Blackboard, you can, or just go back on YouTube and just kind of rewind. The planetary model is going to it's going to have those orbs surrounding the nucleus, and the orbital model is going to have sort of this haze around it, right? And so this would have been A in the previous slide, and planetary model would have been B on the other slide as well. Okay. So again, this is just showing you again the planetary model. Here you can see that you can see two electrons, electron one, electron two. But in the orbital model, there you can't see them. And the idea of it is that you really don't know where those electrons are, right? So you can't say where they are, right? So that's really different between the orbital and planetary model. Again, if I ever show you an atom, it will be, at least in this form, it will always use a planetary model. But just know that you can also uh, 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 illustrate a atom by using this orbital model here. And again, this electron cloud, you can see in this key is sort of in this gray area, really indicating that, hey, we really don't know. We know these electrons exist, but we really don't know where they are. And you may say, well, how do you know how many electrons there are? Well, you know how many electrons there are just by counting the number of protons, right? And so because we have two protons, you know that there are going to be two electrons, right? In the planetary model, it's very easy to see. That's the reason I emphasize that in the class. But in the orbital model, you would just really have to look at the protons there. Okay. All right. So when we look at, so an isotope is when an atom gains or loses a neutron, right? And when an atom gains or loses a neutron, it becomes an isotope. And so many isotopes, some isotopes are stable, like deuterium, right? Which is an isotope of hydrogen. But there are some isotopes that are very unstable, right? Like carbon 14, for example. And so one example would be radiocarbon dating, right? So I don't know if you ever heard of radiocarbon dating, but radiocarbon dating is this ability for scientists to sort of take fossils or bones or artifacts, and you measure them using this machine here, and this machine actually measures carbon 14, right? So I'll briefly explain what it does, but you're not responsible for it specifically, right? So we all in our body have carbon 12, and carbon 12 is very stable, right? It looks stable, six protons, six neutrons. It looks like it's great, right? But we also have this more unstable carbon 14. And when we die, carbon 14 will, because it's unstable, it will decay or radio decay into I think a nitrogen, right? So it actually goes away, right? So the carbon 14 vanishes, and carbon 12 stays the same in our body, right? And so what the scientists can do is that they can take a fossil and measure carbon 12, which stays constant, and compare that to carbon 14, which is always going to be degrading at a specific interval. And just by using mathematics, which is probably beyond my pay grade, you can determine the age of a fossil, right? One cool example would be the Shroud of Turin, right? So, and it's actually a really cool example. And again, you can look this one. You can actually look up the Shroud of Turin. It's actually a really great example of this. So you may or may not know the story, but the Shroud of Turin is this artifact in which it's alleged that during during biblical times when Jesus, and again, hopefully I have the story right, when Jesus was climbing the Temple Mount, when he was going to be executed, he fell any number of times, and a woman, I don't know if it was a woman or a man, I think it was a woman, came up to him and put this cloth over him. And when they put this cloth over him to kind of dry the blood from his face, when they removed the cloth, the idea of it was that his face was sort of etched or sort of emblazoned into this fabric, right? And so in the late 80s, what they did was that they took this Shroud of Turin and they subjected to radiocarbon dating. And what they found was quite interesting. What they found was that this Shroud of Turin was actually made about in the medieval times at around 1300 AD, right? So I mean, that would have been like what, what is it? Gosh, I'm bad at math. 700 years ago, right? But if you guys remember your history, during the date that this would have for this to have been genuine would have had to been about 2,000 years ago, right? So the idea is that it's likely that the Shroud of Turin was a fake, right? That this was an elaborate forgery made by someone in during medieval times, and that it really was not derived from during that time when Jesus was around, which would have been about 2,000 years ago. And again, I find it very interesting. We will not be tested on necessarily radiocarbon dating or on the Shroud of Turin, but I think it's very interesting to kind of talk a little bit about how isotopes can be used to date things, right? And they're also used in medicine as well. Okay, so this is just some examples of isotopes. So, and again, an isotope, so again, this is hydrogen, which is our regular old hydrogen. And hydrogen is weird because it has no neutron, right? So it has one proton, one electron, right? But if you add a neutron to hydrogen, it becomes deuterium, right? And deuterium, believe it or not, even though it is a radioisotope. It isn't radioactive, right? Or if it is radioactive, it isn't radioactive that it kills people. So if you drink water, for example, or your water, so many of your water molecules will contain deuterium. So all of us and everyone who's listening to this, we've all consumed water with deuterium in it. Um, Tritium, on the other hand, is actually very unstable and would kill you, right? Or probably make you very, very sick. And that's because tritium has two extra neutrons, right? And so what ends up happening is that this tritium will at one time will release one of these yellow neutrons, and when it releases it, energy is going to be released, and that energy is radioactivity. Okay. So again, all of these are deuterium and tritium are examples of isotopes. And so the radioisotope, again, as we're talking about, they tend to be unstable and they will decompose to a more stable isotope, right? And so this is an example of potassium 39. So potassium, its weight is 39, and if you add and if you give potassium an additional neutron, it becomes potassium 40. But it really is unstable when that occurs, right? And so it will try to sort of snatch electrons from neighboring atoms, or in most cases, it will then eject electrons. And when it ejects electrons, it will then put out radioactivity, which in many cases can be harmful to biological life. Um, one way of using or harnessing this is to use radioiodine therapy. So what radio and iodine therapy does is that um, you give someone radioactive iodine, and because there's only really one organ in the body that handles iodine, which is the thyroid. If you have thyroid cancer, they can actually give you a radioactive iodine, which will then selectively kill this thyroid, which is here, right? And you can see this is sort of uh, uh, I guess I don't know if it's a CT scan, an MRI of a thyroid, and you can see that a part of this wing, right? So you have one wing here, but part of this wing is sort of damaged here, and that's simply due to the radioactive iodine treatment, right? So this is a way to sort of selectively kill cancers, right? And the reason it's killing it is because something that's a radioactive isotope, when it decays, is going to release radioactivity, which would then kill biological life. And in this case, it's helpful because it's helpful almost as a magic bullet because it's selectively going to kill cancers of the thyroid there. Okay. So now that we talked a little bit about isotopes, I want to go on into molecules and compounds. And again, these are very, very easy. A molecule is if you take two or more of the same atoms, right? So example of that would be you take an H and you add another H and you have hydrogen gas, right? So or if you have O don't laugh at my O's, but plus another O, you can have O2, right, which would be molecular oxygen. So this is actually called, sometimes we actually call this molecular hydrogen, right, because it's two hydrogens, and sometimes when we have two O's or two oxygens, we call that molecular oxygen because it's a molecule, right? So if you have two of the same element, you're going to call it a molecule. Um, and the reactants, which you're going to react, is going to be to the left, right? So these are going to be the reactants, and onto the right of the arrow, this is going to be your product. And again, I know this is all review for those if you've taken chemistry. A compound, on the other hand, is when you have two or more different elements, right? So an example of that would be like salt, right? Na plus Cl, right? That would be if you combine NaCl, which is salt, that will be a compound. And I like to think of it like a compound pharmacy, where if you, a pharmacy that then sort of mixes drugs together for the specifications that your doctor puts on the prescription. Will be a compound. That's how I remember like compound pharmacy and compound. They're going to be something too different. And molecular is going to be same. So molecular is going to be two of the same elements, while compound are going to be two or more different elements. And so keep this in mind because I can't go back, gosh darn it. But just sort of keep that in mind because I will certainly be asking you the difference between a molecule and a compound on the exam. So this is just another example of, and just by looking at this, you have a sodium, right, which we just talked about, plus chlorine, and if you put that together, you actually get a compound, right? And hopefully that makes sense. This is a compound because sodium isn't the same as chloride, and you're putting those together to get sodium chloride. So this would be an example of a compound. Um, and this is just showing you sort of the how this works. That we're going to revisit this back in a little bit. You have sodium, which is going to be here, and you have chloride, which is going to be here, and then there's a transfer of an electron. We'll talk about that in detail in just a moment. And when they come together, you have a compound, right, with sodium chloride. Right, one is going to have a positive charge, and the other is going to have that negative charge. Okay. So electrons are going to occupy energy levels called electron shells, and the electrons closest to the nucleus are going to be the most strongly attracted, rather. And each shell is going to have distinct properties. The first number of electrons has an upper limit, and the shells closest to the nucleus feel first, right? And so that's actually quite important that first shell actually can only hold up to 2, and the other ones can actually hold up to 8, right? And there could be multiple shells, okay? And there's a picture that kind of makes this a little bit clear. Um, and so the cool thing about chemical reactions, so when things come together, like two atoms come together, they're going to be put together through what allows them to react are going to be the electrons, right? And so chemical reactions are going to occur when atoms combine to dissociate from other atoms, and this only is going to be the interaction between the electrons between those atoms, right? And I call them outer shells, but sometimes if you've taken chemistry or you have like an inner chemist in you, you typically may call them a valence shell or just a valence, right? So atoms with a full valence shell do not form bonds. So a good example of this would be like the noble gases like argon or neon or helium, because these shells are already filled with electrons. These do not interact with other atoms. Okay, so there is a rule, we call it the rule of eight. I was always grew up when I was going to college, we call it the octet rule. So I just sort of put them both there. And the whole point of the octet rule is that atoms, so like a sodium and chloride, they want to have 8 atoms in their outermost orbital, right? And so if we look at chloride here, right, you have two, I'll kind of erase that. And So we have 1, 2, 3, 4, 5, 6, 7, right? So this chloride atom has 7 electrons in its outermost shell. And so for it to be happy, it would either need to eject 7 electrons or just gain one, right? So just imagine if your whole life's work is just to get 8 electrons. So, and that's really what these atoms are trying to do. With sodium, it only has 1 electron in its outermost shell. So it would love to get rid of this one because it needs to either gain 7 other electrons or eject this one. And the reason ejecting this one will be okay is because the shell under that has 1, 2, 3, 4, 5, 6, 7, 8. So because there's 8 shells, I'm sorry, 8 atoms, I'm sorry, I'm sorry, 8 electrons in its second shell, if it can get rid of this electron in its outer shell, it will be very, very, very happy, right? And so if you look at this reaction here, that's exactly what happens. The sodium ejects its electron and gives it to chloride, right? And when you look at the resulting reaction, the sodium is going to now have 2, 4, right? 1, 2, 4, 6, 8 on its outermost shell, and chloride is going to have 2, 4, 6, 8, right? And so you may ask yourself, well, why did it become positive and negative, right? So that's kind of strange, right? And the reason it went from positive to negative is because an electron has a negative charge. So by giving up its negativity, it becomes positive, right? So, just imagine you go to a therapist, right? And you're feeling really, really sad and your feelings are negativity, right? So you give your negativity to the therapist, right? Well, now that you've given your negativity to the therapist, you are now positive, right? And now because the therapist has taken on some of your negativity, he or she has now become negative. And again, that's just sort of a very silly way of looking at it, but that's kind of how I look at it because I'm a little weird. Because I always think of like this electron as something being very negative, and by giving away your negativity, you become positive, right? The only exception to the rule of eights is the first shell, and the first shell is kind of this one, right? So I'm kind of highlighting it in here too. And if you and I'm highlighting it in here, and I could highlight it here too. Don't make fun of me. And um, and each of these very first shells can only hold 2 electrons, right? So that's the only exception to the rule of eights is that very, 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 very first shell. Okay, atoms are going to be stable when the outer most shell valent when the outermost shell is complete, right? And that's really the main thing here. Um, Knowing that shell 1 can hold 2, shell 2 can hold up a maximum of 18, I'm sorry, 8, shell 3 can hold maximum of 18. But really, the only one I would ever test you on to know the amount of electrons would be this very first shell, right? So uh, I may ask you, hey, how many electrons can be in that very first shell? And hopefully you will say only 2, right? The one for shell 2 and shell 3, I'm not going to, even though it's important, I would say it is important for you to know, especially for shell 2. I'm not going to test you on that specifically. I'm going to assume that you've already had that in chemistry. And shell 3, again, that's something I'm not even going to touch at all in this class. Okay, so this is an example of a chemically inert element. And so what that means is that this element are very, very stable. And again, these would be examples, these would be like noble gases. All right, so for example, like helium and neon, these are gases that do not react with other atoms. And when they do, they have to be in very, very specific laboratory conditions. And the reason is because they already have the rule of eights, right? Their shells are already filled. So helium, for example, has 2 electrons here, right? And remember that very first shell can only hold 2, and because it only has 1 shell, helium is good, right? It doesn't want to really be with anyone else, right? Imagine if your life's if your life's dream was to only get two marbles, once you have two marbles, you probably don't ever want to talk to anyone ever again, right? And that's kind of how these noble gases work. Neon is similar as well. This outer shell is going to have one, two, three, four, five, six, seven, eight, and because you have eight electrons on its outermost shell, this atom is completely inert, right? It does not want to react, right? And again, this is pretty rare, right? Most atoms have sort of this incomplete valence shell in which they want to react with others, but these noble gases are an excellent exception to talk about because their outer shells are going to be filled, therefore they do not want to react with other atoms. Reactive elements refers to atoms in which the outermost valence shell is incomplete, right? And so what these atoms will do is that they will gain, lose, share, do anything possible to complete their outermost orbitals as having an their outermost shell is either having two electrons or eight electrons. And again, uh, for our purposes, we're just going to use 2 and 8, right? And so when atoms reach a stable state, and the bond formation produces a stable valence shell, right? So many of the bonds that we're going to see, not all, but most of them are going to form these very stable bonds in which the outer shell is going to be complete because many of these atoms are going to end up sharing electrons with one another to complete their outermost shell. Okay. Or orbit. Okay. So this is an example of our chemically reactive elements. And these are atoms that do not have a their outer shell is not filled, right? And so hydrogen, for example, only has one, but it will love to have two. Carbon has four, it would love to have eight. Oxygen has six, it will love to have eight. And sodium has one, it would love to have eight, right? So hydrogen, carbon, oxygen, and nitrogen, I'm sorry, and sodium, sorry, are going to be unstable, incomplete, and they're going to want to react with one another, with each other, with other atoms to either eject, share, gain an electron so that they can be happy or they can be stable. And again, this is all in service of satisfying that octet rule. This is not from your book. I love this slide because it sort of brings these concepts together, kind of comparing sodium and helium, carbon and neon, sodium and argon. And again, all the helium, neon, and argon are all going to be noble gases, while hydrogen, carbon, and sodium are going to be sort of other types of atoms that are going to be reactive or non-noble gases or non-gases. Okay. So when we're talking about chemical bonds, so chemical bonds are going to form when electrons are going to be completely transferred to one another. So in that other slide where the sodium donating its electron to the chloride atom, right? Because the chloride has 7 on the outside and the sodium has 1 on its outside. That's going to be ionic bond. And this is going to one way that they are held together are going to be the charges that are going to be produced, right? That one's going to be negative and one is going to be positive. And the whole point of this transfer is to achieve stability through the transfer of those electrons. Right, and again, ionic bonds are pretty easy to break. In fact, if you add water, water will break apart ionic bonds very easily, right? So we can put like water breaks apart, and um, water breaks ionic. Ooh, this is hard to write. There we go, right? So water breaks ionic bonds, and so these bonds are actually very easy to break. And if you don't believe me, you can take salt, and which is sodium chloride, and you add water, and you can actually see that the salt will just literally disappear in the water, right? And that's because water breaks apart those ionic bonds. All right, so an atom, 'cause remember, atoms are either made out of neutrons, electrons, or protons, right? And if an atom loses an electron, um, it becomes an ion, right? And again, if you're saying, why the heck is it positive? Remember, electrons are negative, right? They're negativity, like, ooh, you being negative. Ooh, quit hating, right? So if someone is negative, and if you're negative and you're giving your negativity away, now you're going to be positive, right? And if an atom is chilling and someone gives it electron, which is negativity or it's negative, you're going to become more negative, right? And that's kind of how I like to think of it, right? That if you lose an electron, the ion becomes positive, and if you gain an electron, the atom becomes negative. And even though these are all ions, both these are ions, they can be broken up specifically. If it's a negative, if it's something negative here, right? This would be negative. That would be an anion, right? And an anion is just going to be it's negative because it's gain an electron. Again, by gaining negativity, the atom itself becomes negative. And a cation, this is going to be positive because it's lost an electron, right? And hopefully this makes sense because electrons are negative. Therefore, if you give up something that's negative, it makes you more positive. How I remember this personally is because I like cats. So I think, yeah, I know a lot of people may disagree, but I figure that cats are very positive, right? Though depending on the temperament of the cat, they may not be. Um, so always think of like positive cats or nice cats. And so cation, I just kind of instinctively think of, okay, this is an ion that has a positive charge, right? So an example of a cation would be like sodium, right? Which has a positive charge, or calcium, right? Which has a positive charge, right? An example of an anion, for example, would be like chloride, right? And the chloride anion, and the reason is because it has this negative charge there. And so when you have a cation and an anion together, they tend to attract to one another like magnets because of those opposite charges. So this is sort of bringing us back to where we were talking about before, the sort of story about this forming an ionic bond. Again, this is a sodium, and it's sort of trying to satisfy the octet rule. The sodium ejects not so much ejects, but gives its electron to to the chlorine atom, and this chlorine atom uh, now is satisfied. And you can see here, once this happens, this chlorine atom is going to be negative, and the sodium is going to be positive. But if you look at both the sodium and the chloride, each of these have 8 electrons in its outermost shell. So even though the charge has changed, they still are going to be happy due to the octet rule of having those 8 electrons in the outermost shell there. So I don't think this is in your book, but I love this slide because it really kind of brings everything home. That if you have an atom, which is here, and you change the electrons, right, you're going to make an anion. I'm sorry, an ion. And again, an ion can either be a cation or an anion, right? So in other words, if you don't like cation and anion, just think of it as the ion is going to be negative, which is an anion, or it's going to be positive, which is a cation, right? So ion is very, very non-specific. Cation and anion is more specific. And again, when you have these ions in the blood or in the body, we typically call these electrolytes, right? These something that these species like sodium, potassium, chloride, calcium, these are going to be electrolytes that have a charged species, right? Okay, and then neutrons, which we just talked about here earlier, if you change the neutron, so if you have an atom and you give it a neutron or you remove a neutron, you're going to cause an isotope to occur. right? So if you change the neutron, you have an isotope, and typically if you do that, you're actually going to make it more radioactive, though not necessarily, right? So for example, in deuterium, deuterium is an isotope of hydrogen. However, it's not radioactive. Another example that we didn't talk about it until just now is protons. So if you change the proton of an atom, you actually change the element, which is pretty cool, right? So in many cases, if you have a periodic table, you could turn if you can add so you start off with hydrogen with one proton, but if you could add another proton, it will turn into helium, right? And if you add another one, it will turn into lithium. If you add another one, it will turn into sodium, right? And so really, if you had a power to do this, you could literally turn silver into gold, right? Because if you silver, which I think is Ag, and gold, which is I think AU, which I may be wrong on that one. But if you could literally add, if you could add the difference between the protons found in sodium to the difference of the protons found in gold, you could literally make turn silver into gold, which is pretty cool though, even though we can't do that. Maybe not yet, but maybe someday. Okay. Um, so hopefully you may want to go back on that section just to make sure that you kind of got that part. It never hurts just to always read the book and to go back if you need any extra help. Okay, covalent bonds, these are going to be much more stable than ionic bonds. So ionic bonds are very weak. You splash a little water on these ionic bonds, and these things are like they gone a bit. They split apart, right? Covalent bonds are very tough. So for example, a diamond, which is made out of carbon to carbon covalent bonds, right? So again, covalent bonds are going to be very tough, and one of the reasons that they're much harder to break is because they sort of equally share these electron pairs, and we'll talk about that in just a moment. Okay, so covalent bonds involve sharing electrons between atoms in a ways that it fills each electron's valence shell. So an example would be like hydrogen gas, right, in which you have H2. Um, and so unlike atoms linked by covalent bonds, they form a covalent compound. Okay, um, and so this is just an example here, and I think if I remember correctly, we're just going to go through these individually, right? So this is a formation of a covalent bond. So you have hydrogen here and another hydrogen here. So hydrogen here. And when you add them together, you have a covalent bond. And these two electrons, they're actually being shared. Oops, let me kind of erase that there. Uh, they're actually being shared, and these are the shared electrons there, right? And so by sharing, they sort of equally sharing these electrons, you sort of have a covalent bond. And so as you see here, there's no plus or minus or no negative, nothing to indicate that it's negative or positive. Therefore, that if you add this in water, it won't break apart. You're going to need something much stronger like heat or pressure to actually drive the separation of these two hydrogen atoms together, and that's simply due to the fact they're bound together through um, uh, 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 they're bound together through a covalent bond. Okay, this is just just the same example, but using a different atom. Again, this is going to be our oxygen. So you can count yourselves, but you have 2, 4, 5, 6. So you have 6 electrons on each atom. So again, they would love to be able to share these electrons to have that stable 8. And you can see that what happens here is that on this oxygen atom you have 1, 2, 3, 4. So these oxygen atoms here are actually sharing 4 electrons. So if you look here, 1, 2, 3, 4, combine that with the 4 that they're sharing, you have 8. And the same thing on this side here, 1, 2, 3, 4. Combine that with the 4 that's being shared here, and you have 8, right? And so again, sort of this sharing of electrons allows for the bond to be stronger, and in fact, and because they're sharing these bonds, there's no differential in charge that occurs. Though if you've taken chemistry, you may have learned something about partial charges and stuff like that, though we will not really be talking about partial charges in this class. Okay, so this is another example of a covalent bond, but in this particular case, instead of forming a molecule, we're actually forming a compound, right? And how we know it's a compound is because you have a carbon here, 1, 2, 3, 4, and again, this carbon will love to have 4 electrons, 4 more electrons to have 8. And these hydrogen atoms, 1, 2, 3, 4, each of these hydrogen atoms only has 1 electron on its outermost shell, therefore that they would love to have 1 each. And if you look at what happens when they are combined, you can see that this hydrogen is sharing 2, this hydrogen is sharing 2, this hydrogen is sharing 2, this hydrogen is sharing 2. So all these are sharing 2. And we can see that now if we count all these 2, 4, 6, 8, the carbon is happy and each hydrogen is going to be happy too because they get to have, they're sharing 2 as well. 2, hydrogen sharing 2, this hydrogen is sharing 2, this hydrogen is sharing 2, and this hydrogen is sharing 2, right? And so in this case, you have sort of this covalent bond. We have this equal sharing of electrons between these atoms here, thus satisfying the octet rule. Okay, so covalent bonds can either be polar or nonpolar, right? And polarity is just going to refer to the electrical charge on one end of the molecule compared to the other. So when a molecule is polar, there is going to be an unequal distribution of charges, right? And when something is nonpolar, the distribution of charges are going to be equal, right? So a good example of something that's polar would be like water is like slightly polar, or actually, a lot of molecules, or I think most molecules are pretty much are polar in a way. There's sort of an unequal distribution of charges, right? Non-polar molecules, they tend to be more fats, right? Cholesterol, for example. And this is when a molecule would be equal, right? So a good example of this would be like sort of pharmaceuticals, right? So for things to pass to the from the blood into the brain, they tend to need to be nonpolar, right, or lipid soluble or nonpolar, and and so, for example, if you wanted to be wanted to go into drug discovery, if you want something that targets the brain, you need something that's going to be nonpolar, right? Something. Ooh, let me just. You need something that's going to be nonpolar. Um, and because something that's polar will not go through the brain, go through the blood brain barrier. And so a good example I like to bring about this is Imodium abuse in teenagers, right? And you can type Imodium abuse online and you'll come up with some interesting news articles. But Imodium, which you may not know, is an over-the-counter drug for diarrhea, and you take it. And what Imodium does is that it's actually an opioid, right? It's kind of weird. And it's an opioid that is extremely polar. And when Imodium is taken, it does not bind, it doesn't go to the brain, but it does bind to opioid receptors outside the brain, right? And so, and this is just an example of that. If you want to design a drug that affects the body and not the brain, you're going to want to make it polar. But if you want to design a drug that enters the brain, you want to make it non-polar, right? So I know the only reason you're not going to be testing on that specifically, about drug design and all that, and whether it's polar or non-polar. I'll only tell you this just so that you know that it actually means something, right? Another property of something when it's polar, typically when something is polar, it's typically kind of targeted for excretion by the kidneys, right? When something is made non-polar, you kind of then sequester it into the body. So a good example would be like vitamin D, for example, is non-polar. Vitamin A, vitamin E, I think I already said D, K. Those would be nonpolar molecules. Therefore, you tend to store a lot of these molecules in fat, right? And that's just simply because we tend to sort of hold on to nonpolar molecules while polar molecules tend to be excreted out. A vitamin that's example of a polar molecule would, ooh, sorry, I went ahead. The example of another polar molecule would be the B vitamins, right? Which if you take one, you may notice that your PP is yellow, and the reason it is just simply because we readily excrete these polar molecules. Okay, so this is carbon dioxide, and as you can see, there are no pluses or minuses here, so therefore, this is going to be a non-polar molecule, right? So this is going to be non-polar. And I like to think of polar, you know how sometimes they say like America is polarized politically, right? Well, think about it. Non-polar would just means that you're not polarized, right? Polarized would mean that you are kind of separated on some axis, right? On some cleavage. Okay. Um, Okay, and then this is water, which you can see these partial positive and partial negative charges here. Therefore, this would be a polar molecule, right? So water is going to be polar. And again, water is very special. So water, even though it's polar, water can actually go from the blood to the brain, right? But just know that even though water is polar, it's a very, very special. I was actually going to say molecule, but it actually is compound, right? Because you have two hydrogens and one oxygen. Okay. Hydrogen bonds, in comparison, are going to be very weak. Um, and so they're going to be responsible for the attraction between molecules. Hydrogen is going to be attracted to the negative portion of a polar molecule, which we're going to talk about in just a bit. And in fact, hydrogen bonding is really how water has this tendency to sort of bead, right? Because water is attracted to itself, right? Because water has a negative end and a positive end. And so because water is attracted to itself, if you put a piece of water, if you kind of spill some water on a table, depending on if it's just the amount of it, a lot of it may just bead right on that surface. And the reason it would bead is because water is attracted to itself due to the negative and positive charges that it has. Um, it also provides, so we just kind of talked about that one. It also is involved in the surface tension of water, right? So there are some insects, for example, that when they're on water, they don't just fall into the water. And the reason they don't fall into the water is because they're so light that they actually do not displace the hydrogen bonds, the bonding between water, right? But however, we humans, we're much, much fatter and bigger and than insects. Therefore, that when we get in water, surface tension doesn't really matter to us, right? We fall right through the water. But if we were like an insect, depending on how our um, uh, uh, how depending on how our arms and legs are, imagine we're insects, we may be able to actually walk on water. Um, Hydrogen bonding is also important in forming those intermolecular bonds and protein structure, right? And we'll actually talk a little bit about that later. Okay, this is what I was talking about before. I kind of jumped ahead of myself. So, you see how water will orient itself. So you have positive, positive, and then the positive will be oriented to the negative, and to the negative here, right? And then the negative of the hydrogen will be oriented to the positive, the hydrogen here, and the positive, the hydrogen here. So water is kind of weird because water has like negative and positive sides, right? Which is kind of funny. I know this sounds kind of weird, but just imagine if you could be a male or a female, right? Depending on who you were with, right? And that's kind of how water is, right? Water is very flexible, right? Meaning that water can sort of form hydrogen bonds with itself or with other compounds or molecules. And this is what I was referring to before. This insect, it's so light that it actually can't displace the hydrogen bonds between the water. Therefore, it actually can walk on water, right? And again, you have to be very, very light to be able to do this, right? And obviously, humans, we don't have this capability. Okay, so remember that electrons are going to participate in the formation of chemical bonds. Um, and then the octet rule, or the rule of eights, the atoms are going to want 8 electrons in its outermost shell. And with these electrons, 8 electrons, the atom is going to be considered stable. Now, do remember that that very first shell is going to want 2, right? But after that, it's going to want 8. And so atoms will do anything. It will kill its mom. It will, like, rob its dad. No, I'm just kidding. But it will lose, gain, or share electrons with any other atoms to achieve that stability. And really, once it changes that has that stability, it's good, right? It doesn't really want to react with anything else. Okay, so let's talk a little bit about chemical reactions, right? And um, so with chemical reactions, you have synthesis reactions, in which atoms or molecules are going to combine, right? So you take A plus B, and then you get AB, right? And energy is actually going to be needed for these reactions, right? So you're going to need some type of energy to drive to actually combine A and B to turn it into AB. And this is going to underlie anabolic activity. So anabolic just means to build up. I like to think of like anabolic steroids. So if you think of anabolic steroids, you probably think of someone who's taking these drugs that are increase muscle growth. And that's going to be that's going to underlie synthesis reactions. Decomposition reactions is when you have AB, right? So you basically take this and then you want to break it back. You want to reverse the synthesis reaction. So you take AB, and then what occurs is that you break A and B from one another to turn it into A and B, and then energy is going to be released, right? And so synthesis is energy in, decomposition is energy out, right? And this is going to underlie catabolic activity, right? So when your body is breaking down things, right, this is going to be catabolic, right? So anabolic is to build up or to synthesize. Catabolic is going to be to decompose or to break down, right? Again, synthesis is going to require energy, while decomposition is going to release energy, right? So when you have ATP, when ATP goes to ADP to release energy, that's going to be a catabolic activity. All right. An example of synthesis would be turning glucose into glycogen. So glucose is in sugar, and glycogen is how we store glucose in the liver, right? And that will be a synthesis reaction. So this is just an example of a synthesis reaction here, where you have amino acids. So amino acids are found in like meats, for example, and combining these amino acids actually will make a protein, right? And this is going to be called a synthesis reaction, right? So you have these little monomers, right, all over the place. And when you combine these monomers together, you make a protein, this large protein. And this is clearly you're synthesizing something, like you're taking a bunch of beads, let's just say you have like a bunch of pearls that are just all over the place, and you're kind of putting them together, right? You're kind of synthesizing or building them up. And this is called a synthesis reaction. A decomposition reaction will be glycogen, right? So again, I just talked about this before. Glycogen is really how we and other animals store glucose. We store it as glycogen. Glycogen looks like this. And when we're sleeping, for example, because we can't eat while we're sleeping, at least most of us can't, we will take glycogen and then break that down, and then energy will be released as well, right? So again, decomposition reactions, synthesis reactions are like yin and yang, right? They're literally the opposite of one another. Okay, there's a thing called an exchange reaction, and this is a reaction that is both synthesis and decomposition, right? So just imagine that A and B are together, right? And then C is sort of alone, right? Sort of the third wheel. And now A dumps B, and so A is now with C, and then B is alone, right? And so it's both synthesis and decomposition because you're synthesizing A and C, right? But you're also breaking down or decompositioning A and B. Does that make sense, right? Another example would be in this example with A and B and C and D. So imagine A, B are together, C, D are together, and now A and D are together now, and while C and B are together. So what's happening is that you have an exchange reaction. You're both decomposing these reactions, right? You're breaking them apart, and then you're reforming them through synthesis reactions, right? And so this switching is just refers to an exchange reaction. And again, on the exam, I may put up like A plus B. I may actually may put this up here and say, hey, what type of reaction is this? I may say, is it exchange, synthesis, decomposition, or none of the above? So just kind of keep that in mind not only knowing the definition, but being able to identify if I were just to use this AB plus C equals AC plus B, or I could use even like AB plus CD equals AD plus CB. So just kind of keep that and tuck that in the back of your mind for the exam and quiz. Right. Probably the most famous exchange reactions would be making ATP, taking ATP and putting a phosphate on glucose, right? So again, you have glucose plus ATP, and what occurs is that ATP will donate a phosphate group. So it actually gives a phosphate group to glucose, like so. And then now you have there's a glucose phosphate and ADP, right? And you can see that the difference between ADP and ATP is really this loss of a phosphate, right? And so this again is just an example of an exchange reaction. Okay, so most chemical reactions are going to be reversible, and reversibility is going to be indicated by a double arrow, right? So when the arrow is going to differ in length, or the longer the arrow indicates the more rapid the reaction or major direction of progress, right? And so you can look at the factors that influence this on the table 2.4 in your book, but actually I think that's on the next slide here, right? So these are going to be the factors that are going to increase the rate of chemical reactions. So one factor that increases the rate of chemical reactions is an increase in temperature, right? So it's very cold outside, so the atoms outside are actually moving very, very slowly, right? And so think about your refrigerator or your freezer, right? If you were to put meat out in hot weather, what will end up happening is that the heat the heat around is actually going to sort of speed up decomposition of the meat, right? But if you put that meat in the freezer for storage, you're drastically slowing down the atoms that are kind of spinning in this dead ground beef. Therefore, you're going to decrease the rate of decomposition of the meat, right? So if you increase the temperature, what ends up happening is that you increase the ability of the atoms to collide, and when they collide, they can actually then make form reactions, right? And this is why, if you've taken chemistry, many times you can increase the rate of a reaction by increasing the temperature of the reaction. Another way to increase the rate of a chemical reaction is to, I mean, kind of, one way to also increase the rate of the chemical reaction is to increase the concentration of particles, right? So if you increase the amount, if you're using sodium chloride, like sodium, let's say HCl plus, well, it'll be HCl plus, oh gosh, sodium hydroxide. Uh, what you can do is that you could what you do is if you can add more of one of the reactants, like hydrogen chloride, you actually will increase the rate of reactions because there's more of the reactants to work with, they have a better chance to be able to collide, right? And so that's an example of that. Another one will be particle size. So if you make the particles smaller, they're actually going to have more kinetic energy and they're going to move faster and they're going to have more chance to hit each other in collisions, which will allow it to make sort of make these reactions occur and happen. The other one is the presence of catalysts. So we'll talk about that later. But catalysts are going to be found in like enzymes, for example. And what they do is that they're not used up in the reactions, but they sort of help a reaction take place. And then they are actually able to do it again and again and again and again and again. A good example of this would be the catalytic converter in many of your vehicles. What the catalytic converter does is that it converts carbon monoxide, which is a very dense poison, into carbon dioxide, which is also a poison, but it's also a greenhouse gas, but it's less of a biological poison, right? And again, if you have a catalytic converter, which I think is made out of like palladium or gold or silver or some kind of precious metal, that catalyst is never used up. It's not used up. It's there to actually participate in the reaction, and that presence actually speeds up the ability of this reactions to keep going on and on and on and on, right? So again, don't really get bogged down on necessarily the mechanisms. Just be able to know that these are going to be really these four factors that are going to be involved to increase the rate of chemical reactions. Okay, so let's talk a little bit about water, right? So water is very, very special, right? Water is the most common substance on Earth, and it has a positive end and a negative end, right? And the oxygen atom is going to be negative, while the hydrogen atom is going to be positive, and so this makes it so that water has this property of polarity. And this polarity is really allows us water to act as a very good solvent, and sometimes we call it the universal solvent because water can break apart many, 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 many molecules, except nonpolar molecules, right? So if it's nonpolar, water can't do nothing with it. But if it's polar, water can actually act as a solvent. It can actually dissolve what you're trying to put into it. So water is a universal solvent and it's required by all organisms and it's very, very special. So water has some four properties that we go over in the book. One is polarity. So water has this ability to attract and break apart other polar molecules. The other quality or property that water has is a high heat capacity. So water hydrogen bonds will actually absorb heat when they're broken and then will actually release heat when they're formed. So this actually underlies a lot of the sweat that occurs, right? The property of sort of cooling, right? When we are hot, when water goes from a liquid to a gas state, it actually will absorb a bunch of heat before when it's broken, before it turns into a gas, right? So it's sort of like kind of, oh, in my mind, I think of the water molecules on our body, on the surface of our body when it's hot, sort of shaking a lot, and then they shake so much that they poof, like sort of they vaporize, and when it vaporizes, it kind of sucks up all the heat around it, and when it sucks up all the heat around it, it actually makes us cooler, right? And so this is why if you're hot, it doesn't matter whether you put water on yourself to make you cool or you sweat, it still works as it still helps in cooling the body. The other thing that water does is that it can be a reactant in most chemical reactions. So in the body, water, like the blood and even the cytoplasm, which is sort of if you don't know what cytoplasm is, it's okay. Cytoplasm is just the watery internal environment of the cell. Water acts as sort of this reactant environment, right? It's almost like the air, right? But along with that, water can also be used to break apart molecules, and we actually use that a lot. And it's actually called hydrolysis, right? Hydro water, lysis is a split apart, right? So our body has enzymes that can hydrolyze or use water to basically break apart other molecules. Okay, and then cohesion, I've kind of hinted at this before, that water holds itself together, and the reason it holds itself together is through those hydrogen bonds. Water loves itself, so if you put a little water on the table, water will bead. When I say bead, it just sort of like, looks like little beads of water, and the reason it does that is because water loves itself, right? And so this property of beading or holding together allows it to act as a lubricant against friction, right? Okay, so water has this also has high specific heat as well, and this is very intuitive, right? I mean, it's almost silly for me to even put this on here, but it takes a lot of energy to heat up water, right? And just think about this, like if to boil water is like ridiculous, like 200, like how many degrees is like high 100s or like all like low 200 degrees to heat up water. Air does not take up that much energy to comparatively to heat up. So if this is a very easy question, but if I were to ask you if it's 90 degrees in Wisconsin, if you look at the water, will it be higher or lower? And hopefully you would say lower, because the temperature of water will always be lower than the surrounding air or land, right? Because water takes a lot more energy to heat up than air or land. Okay, this is what we had kind of hinted on before, that if you put salt, sodium, and chloride together and you put it in water, water will sort of arrange itself to dissolve it, right, or to sort of sequester it. So you can see when you put sodium chloride which is salt, in water, the negative ends of the sodium will sort of surround this sodium atom, sort of sequestering it away, and the chloride atom, which is negative, will be surrounded by the positive hydrogens on this water, which will then sort of sequester it away. And so this is really just sort of kind of shows you in a picture form how water can dissolve these ionic bonds or ionic, yeah, just ionic bonds here, right? And really why it's called the universal solvent, right? Because it can dissolve many, many, many of these polar molecules and compounds. Okay, so a polar molecule, which is here, so I think this is ammonia, but don't laugh at me. And ammonia here, you have, I think it's ammonia. This is nitrogen. You have your negative charges on your nitrogen, and you have your positive charges on your hydrogen. And what happens here is that water will orient its positive charge to be with the negative charge of the nitrogen here, but the hydrogens will be oriented toward the negative charge of the oxygen here, right? And this works to essentially then keep this in solution, right? So this is how a polar molecule or a polar compound can dissolve in water, right? Because no matter if it's negative or positive, water will sort of grab onto it and hold it. Okay, so let's talk a little bit about acids and bases. So acids and so when we talk about acids and bases, we typically use a pH scale, and pH literally stands for the pH of hydrogen. I'm not pH of hydrogen. I'm sorry, power of hydrogen, and the pH scale is logarithmic, right? And so the substance with a pH of 2 is 10 times as basic as a substance as 1, right? And what this means is that if you have a pH of 0, you have lots and lots and lots and lots of H's. And if you have a pH of 14 here, you have lots and lots of OH's. So I'll put an OH here, and up here will be put our H here, right? And if you have a pH of 7, ostensibly you would have equal amounts of H and OH. So always think of H is going to be your acid, right? If it helps. And really, if you go on and take other classes, especially medical classes, this will actually help you when you think of like a hydrogen. Okay, so yeah, and I actually like this other slide much, much better. I think this slide is not in your book, but I have really, really love this slide. And the reason I love this slide is because it's showing you that at a pH of 0, you have lots and lots and lots and lots of hydrogen, right? But you have very little OH. And at 7, you can see you have about 50-50, right? Half H, half OH. But when you're at 14, you have lots and lots of OH, but very little H, right? So um, hopefully that makes a little bit of sense. And pH is very, very simple. It's just something that it may take some time just to sort of like stare at it. But really what you're looking at is really the power of hydrogen. So just know that one thing I will just tell you right off the bat, that if the pH is low, that means it's acidic. If the pH is high, it means it's basic. And the reason I say that is because a lot of students will kind of think that if something is high, it means it's acidic, and if it's low, it's basic. So just kind of keep that in mind that, again, I'm going to repeat it, that if the pH is going to be low, it's acidic, and if the pH is high, as in like 14, it's going to be basic. And again, if it's going to be something around 7, it's going to be neutral. What I will say is that human blood is about 7.4. So if it's 7.4 and you were to do a number line, right? 7.4, is it closer to 14 or closer to 0? Well, hopefully you said that it is closer to 14, right? And so blood is actually slightly basic, right? So just kind of keep that in mind and put a pin on that, because we'll come back and revisit that later in the semester. So this is just what I was referring to just a minute ago, that if it's a neutral solution, which is the pH of 7, you're going to have equal concentration of hydrogen ions, right, which is going to be H, and hydroxide ions, which are going to be OH. Right? In an acidic solution, you're going to have lots of hydrogen ions, right? And that's going to be higher than the hydroxide ion here, right? And the same thing with the basic solution, hydrogen ion concentration is going to be lower than the hydroxide ion concentration. And oops, well, you know what I mean. And the main thing is really this, right? Acidic solution is going to be higher. Hydrogen ion concentration is going to be higher than hydroxide ion concentration, and the base solution, the hydrogen ion concentration is going to be lower than the hydroxide ion concentration. So again, acidic is going to be less than 7. And so again, if you're going as you're going low, if you're going from 7 to 0, it's becoming more acidic, and if you're going like from 7 to 14, it's actually becoming more basic. Okay, right. So again, the concentration of hydrogen ions is what determines how basic or acidic it is, right? If you have lots and lots of H's, it's going to be very acidic. If you have very little H's and lots of OH's, it's going to be basic. And the pH scale runs, and this is supposed to be like a straight line, but it isn't. It's going to run from 0 to 14, right? And in the middle would be 7. Right, so if it's 0, toward 0 is going to be acidic. If it's going to be toward 14, it's going to be basic, and in the middle, it's going to be neutral. Okay, and again, blood is about 7.4, and that's going to be slightly basic. Okay, so buffers are going to minimize pH change, and we aren't going to go in too much detail about this, but I do want to talk a little bit about it, right? So the pH in human blood is about 7.4, and it has to be maintained within narrow limits, right? So if you, it really is going to be between 7.35 and 7.45, right? And anything below or above that, you're kind of in danger, right? And so a buffer is a substance that resists changes in pH when an acid or a base is added, right? And so an example would be carbon dioxide. So carbon dioxide is an acid, right? And that will react with water to actually form a weaker acid, carbonic acid. So how about that, right? So you have carbon dioxide, which is a kind of a really strong acid, and then you add a little bit of water, and then you have a carbonic acid. And what's very interesting is that if you ever have pop, or I don't know, or soda, depending on how you look at it, it actually may have a carbonate or carbonic acid in the pop. And what happens is that when you open the pop, that fizz on the tongue and all that stuff, carbonic acid rapidly turns into carbon dioxide, which is the bubbling, and water, right? And so that's just why if you let a can of pop or soda sit, even though maybe you didn't drink any of it, it may be flat. And the reason it may be flat is because as this carbonic acid has been added to the pop, and there's no more fizz left, now you have a bunch of water left that's been put into the pop due to the reaction, and therefore it may taste flat and even diluted, right? Um, and another thing about this buffer, though, I don't think we're going to cover it too much, that this carbonic acid can actually be turned into a base, which is bicarbonate, and then an acid, right? And so this is actually kind of a very cool reaction where you're actually turning something that's something that's into something from a I'm sorry, you're turning a pretty strong acid into a base and kind of a weaker acid right there. And this is all, and these buffers are there to prevent blood from changing pH in sort of these wide swings, right? So by having sort of this carbon dioxide and water, carbonic acids or bicarbonate, and you have enzymes that regulate this, it keeps pH in a very narrow range. And if that seems a little esoteric, don't get too bogged down on it, I promise. Just kind of think of it, just know that buffer is going to be something that resists changes in pH when an acid or a base is removed, right? And it often includes a weak acid or a weak base. In that case, this would be carbonic acid, which is a weak acid. Okay, so when an acid and a base are going to be mixed in water, anions, which hopefully you know will be something a negative, are going to form with the acid, and cations, which hopefully you know will be positive, and that's going to combine to form a salt, right? And so this is a good example of that. HCl plus NaOH equals H2O and sodium chloride, and the sodium chloride is that salt that you know and love, right? That Morton salt. Okay, and so when a salt and acid are going to be dissolved in water, these are called electrolytes. And in fact, if you ever had like electropedia, like Pedialyte, for example, Pedialyte is kind of a drink for infants and toddlers for them when they have diarrhea. And what you're doing is that you're replenishing these ions that they could have lost through diarrhea, right? And the cool thing about electrolytes is that they conduct electrical currents, right? So, and that's really the main thing about that. That again, if these dissolved salts that are going to be in blood are going to be electrolytes, and they can conduct electrical currents. Okay. And again, we've kind of like rehashed this over and over again, right? Where the salt donates or the sodium rather donates its electron to the chlorine atom. Now the sodium is very happy. It has 8 on this outside. It's positive. This chlorine is going to be happy because it has 8 on its outside as well. Though the charges have changed, right? The sodium is now positive because it's given up its negative electron, while the chlorine, on the other hand, is negative here because it's received a negative electron. You can see here from the chlorine, so you can see that it's going to be negative here. Okay. Um, so so chemical reactions, right? We have chemical reactions. Many things that we're going to find are going to be like polymers. They're going to be like these chain-like molecules that are going to be made out of many similar or repeating units called monomers. And I would think of a monomer as like a building block of a polymer, like or a Lego of something, right? And many biological molecules are polymers, such as carbohydrates and proteins. And one way that we make these is going to be like dehydration synthesis, right? In which we take a monomer and make a polymer. And then, but we do that through actually removing water, right? And that's why it's actually called dehydration synthesis, right? Because you're removing water to cause two monomers to be joined together, right? So, and again, as you can see here, when these monomers are going to unite, water is going to be released. And this is a picture, and I love this picture. I think this is from your book. You can see monomer 1 here, monomer 2 here, and again, you see the OHs, so OH here and OH here. And again, when you want to join these two monomers together to kind of form a polymer, what you do is that you put these two together, and then the body will then, or the reaction will remove water, H2O. Water it leaves out of the reaction, and then now you have these monomer 1 here and monomer 2 here, and they're going to be linked through this oxygen atom here. And this is called dehydration synthesis because you're removing water from this reaction. The opposite of this would be hydrolysis, right? Remember, I just talked about that earlier. Hydrolysis is when you're using water to split apart molecules. And so you can break down a polymer or monomers put together through the addition of water molecules. And so when a water molecule is added to the bond, the monomers are going to be. Okay, so hydrolysis is really the opposite of what we've just seen before. And this is what I kind of alluded to, how many times enzymes and catalysts can use water to break apart monomers or molecules, right? So you have monomer 1 and you have monomer 2, and what the body or the reaction will do is that it will take water, and it will then water will then be added to this oxygen here, and then it will break apart these monomers that were once joined. So you can see that they were joined, and now you add a little bit of water, and then that actually breaks apart the molecule. I'm sorry, the polymer into monomer 1 and monomer 2. Yeah, I'm sorry, my little arrows are not looking good today, right? But monomer 1 and monomer 2. So this is hydrolysis. So again, you may want to flip back and forth to look at the dehydration synthesis, in which you're taking two monomers and you're linking them together. Water is leaving the reaction. Hydrolysis, on the other hand, is that you're taking these polymers together, adding water, and then breaking these two monomer, breaking this polymer into two monomers, which you can see here. Okay, so I am actually going to stop there, and then what we'll do is, hopefully, if there is going to be class on Monday and Tuesday, we will, after we do a brief review of this other stuff, we will kind of jump right into the slide. Okay, thank you, and stay warm. Bye.